Where's the button?
This thing doesn't allow me to change sides?
Yeah, no, it does, but you have to point it back there.
Oh, okay. I thought this displayed it, but okay.
It works sometimes. It's a 2-degree window. There you go.
This is going through the satellite.
The arrow keys, okay.
You got to push the bottom of your press the button.
Ah, okay. All right, anyway, I'm going to give a brief introduction to the talk. I'd rather not have to do this, but there's still some questions in some people's minds about the quality of the LEND data, so I want to spend a few minutes just showing you that, in fact, we really do have very good quality data. So the reason we have to do this is the last LPSC, they had a session on lunar volatiles. I imagine a fair number of you were probably at that. They had a couple of talks that really had nothing to do with lunar volatiles. They were just critical of the LEND data. We didn't get a chance to have a rebuttal, so to some extent this is the chance here. In addition, just recently there was a blog on behindtheblack.com talking about Igor's presentation. Paul Spuda sent in a comment that he neglected to mention yet another possibility, that this paper and its conclusions are seriously flawed in almost every respect. I'm kind of thinking we should be beyond this, but unfortunately we're not. Okay, so a few things I can show you. We do have excellent spatial resolution. What's plotted here is LEND data in red. This is along the 45-degree longitude line over the pole down the other side at 225 degrees longitude. This is Shoemaker Crater. You see we have a very, very significant suppression of neutrons. It is matched exactly by the topography of Shoemaker Crater as shown by the LOLA data plotted on that axis. Relative to the low hydrogen region, which is at low latitudes, that defines the 0 scale on this, and this is our error bar. This is about a 12 sigma event. Even if we say this is a true baseline for that local region, we still have an 8 sigma event. This really can't be by chance, and especially the fact that it lines up exactly with Shoemaker. You can really take this one to the bank. Okay, others have said our resolution really shouldn't be very much better than that of Lunar Prospector. And here's the Lunar Prospector data plotted for exactly that same longitude line. You can see that there's really no comparison. We do smooth the data in order to get a reasonable signal-to-noise ratio. This is the size of our smoothing diameter. We've been criticized for the fact that smoothing can introduce artifacts. So on the next slide, I'm still plotting for reference the smooth data, but here I took 4 rings or annuli centered on Shoemaker Crater and just averaged the data in those different rings, and these are the values plotted here. They do show relatively large uncertainties, but there is a very clear suppression there. This gets around the problem you have when you smooth. You build up your statistics, but you degrade your spatial resolution the more smoothing you do. There we go. Okay, so to go on, I fit those 4 points to a Gaussian. The width of the Gaussian is 6.4 kilometers. When we convert that to a half width for half of the counts or half of the area of the Gaussian, it's 4.3 plus or minus 1.2 kilometers. Before launch, we cited our spatial resolution, again, at the half area point of being 5 kilometers. So we're actually measuring now on the moon a spatial resolution that's comparable to, in fact, slightly better than what we claimed at the time of launch. Another thing, the statistics, I recognize, I've been working with counting statistics for a long, long time. I recognize that sometimes there can be other sources of error besides just counting statistics. Well, you can do a chi-squared test, and that tells you if the scatter in the data is what you would expect from the uncertainties or whether you've got more scatter that you haven't accounted for. Here, this is a chi-squared probability distribution for any case where you have 14 degrees of freedom. In my case, we've averaged 15 numbers together, gives you 14 degrees of freedom. You could get the same thing if you're fitting a curve to some data. In any event, a chi-squared should typically come out to be about 1 if the scatter in your data is more or less as the uncertainties would predict. It'll never or seldom be exactly that. This is the probability distribution. You could get a chi-squared of 2, and it doesn't necessarily mean things are bad, but that should only happen about 0.5% of the time. So if you make the measurements quite a few times, you can test to see how well you're doing. And it turns out we've done that. There's one place where we had to average 15 points over 3,000 times, so we got some very good statistics. I determined the reduced chi-squared for every one of those 3,200 points, made a histogram of them and plotted them over the blue curve, and you can see it falls right on the curve. This curve is not fit to the red points. There's no normalizations involved here. It really shows that our uncertainties are accounting for all of the noise, all of the random uncertainties in the data. Okay, finally, the last thing, at the LPSC, Vince X showed a graph or a map like this of the first half of the mission and the second half of the mission and said, this is really just noise. The first half of the mission should look just like the second half of the mission. Well, yeah, it is noise because it's plotted on such a fine scale. Those of you in the back, in fact, probably those of you in the front can't read the numbers, but this goes from about 3.8 to 6.2 counts per second. So a huge dynamic range because there is a lot of noise here. The biggest suppression we see is only 0.2 counts per second, so it's not going to show up on this kind of a scale. There we go. Okay, so after you take those same data and you smooth them, and you get a map that looks like this, where you have some substantial depletion in the epithermal neutrons. This is Shoemaker, this is Cabellas over here. We also can make a map of the uncertainties. So we know the uncertainty at every point on the map. The count rate maps are running 5 counts per second on down quite a bit lower to as low as 4.8 for the very low points. The uncertainties, again, you probably can't read those from the back, but it's in the order of 0.01 to 0.02 counts per second, about an order of magnitude less. So in summary, our LEN maps really, if you have the proper smoothing, show statistically valid suppressions, spatial resolutions just as advertised, uncertainties are properly estimated, and they do account for all the scatter in the data. So we really do have a good data supply here, and Max is now going to talk about some of the wonderful things we can learn from these data.
In my part of the presentation, I try to concentrate on the science result, which can be derived from the land data. And I start from this slide. More than 2 years ago, it was discovered that in terms of the global maps of the epithermal neutron flux, we may see the significant depression of the neutron flux around the moon poles, starting from the 70 or 70 degree of the latitude on the south and on the north. It was done by the Neutron spectrometer on board the Lunar Prospector, and now on board Aileroid, it is confirmed by our data from the actually the same detector, which is the omnidirectional detector with the resolution which is comparable with the altitude of the orbit. In here you may see the two maps. One map derived from the land data omnidirectional sensor, which is shown on the left part of this slide, and the map which is derived from the Lunar Prospector data, which is shown on the right part of the slide. And you may see that the pattern of the Newton distribution around these poles is actually the same on the both maps, and the deep blue features on this map shows the most hydrogen-rich areas. This is for the north, and the next map is shown for the south. So we may say, based on this discovery, but that there are two possible sources of the hydrogen on the moon. The first one is the water which may came from the impacts of the volatile-rich comets or the meteorites, and the second one is the solar-driven water, which is the hydrogen created in the subsurface due to the interaction with the protons of the solar wind or the solar particle events. And these hydrogen volatiles can be accumulated in the cold traps in the quantities which is comparable with the prediction derived from the Neutron spectroscopy data. Also, we may say that there are several tunings during the recent time, and one of them is the observation of the infrared area by the infrared spectrometers, which shown the presence of the top layer, which is rich on the hydrogen, which is gradually increasing toward the poles. Also, there are the joint efforts of the two missions, the Lunar Reconnaissance Orbiter and the L-Cross missions, which is provided the most direct evidence of the presence of the water, which is done by the impact to the Cabeos crater, and the observation of this impact shows that the water in this area may be estimated as high as about the 6 weight percent, which it was done by an instrument on board on the L-Cross spacecraft. So we may conclude that enhanced content of the hydrogen or possibly water ice, it is experimentally proved at least at the one local spot, and this spot it is detected in the Cabeos crater. So we may continue the study and may ask the several questions which is in front of us. If the possibility that there are another spots of the water-rich permafrost at the lunar poles, can they coincide with the permanently shadowed region, and how much these water-rich spots may contribute to the total quantity of the polar water at the moon. Here we may use the data from the land instrument, because land equipped not only the omnidirectional sensor with the maps which have been presented on the previous slide, but also with the collimated detector, which is Bill was talking several minutes ago. And this detector has a quite small resolution in terms of the Neutron spectroscopy data, and this resolution, spatial resolution, is comparable with the possible local spots which we are looking for the hydrogen enrichment. So here you may compare the two maps. One map, which is shown on the right part of the slide, is the map derived from the omnidirectional sensor, which is like LPNS, like land, which shows the distribution of the hydrogen in the South Pole with the resolution somewhere between the 50 or 70 kilometers. And on the right part of the slide, you may see the map derived from the collimated sensor for the same area. And here I have shown by the red circles the most interesting areas, which is the quite large polar shadow region, Cabeos, Howard, Shoemaker, and the Palestinian. So the first question which we'd like to ask is to test the hypothesis that water ice deposit may exist in the cold traps of the permanently shadowed regions. This is a schematic illustration how we are doing this analysis. So this one showing the polar extended suppression by the yellow color, and we are looking for the some signal deviation, neutron signal in the vicinity of the permanently shadowed region, and try to estimate how this signal from the permanently shadowed region is showing significant difference in the comparison with the sunlit vicinity of this permanently shadowed region. So we have made such estimation for set of the large permanently shadow region which have been derived from the LoLa data, and have found that there are several examples like the Shoemaker or Cabeos, which showing the significant suppression in the neutron flux in the comparison inside the polar shadow region in the comparison with the vicinity of this polar shadow region. And we may say that the potential candidates showing the presence of the water ice in these regions. But the other polar shadow regions do not show this effect, and we cannot say that we see the significant difference in terms of the Newton signal in these polar shadow regions. We may illustrate this issue by these figures. The first one is shown for the north and the second one is shown for the south. The x-axis on each figure correspond to the exposure time, and the y-axis correspond to the suppression of the Newton flux measured in the persons. So each dot on this charts correspond to the one particular permanently shadow regions, showing showing presence is Newton suppression versus the exposure time, and the dashed line correspond to the statistical significant level. Then we may say that this suppression is significant. So you see that only Cabeos and the Shoemaker and Razdetinsky on the north demonstrate the significant Newton suppression in the polar shadow regions. We also may perform the collective estimation of the possible Newton suppression inside the polar shadow regions. We may combine the several large polar shadow regions with a surface area more than 200 kilometers, which is significantly more than the land footprint, and the distribution of the Newton suppression parameters shown here on this figure by the solid line, which is shown by here. We also may compare this distribution. You see that this distribution is shifted in the comparison to the zero, and the average Newton suppression is a negative, which showing that in average the Newton flux inside the polar shadow region is less than the Newton flux outside this polar shadow region. The dashed line showing the prediction numerical simulation of the counting rate based on the outside vicinity of the polar shadow region, and when it was shifted to the left to try to find the best correspondence between the real distribution of the counting rate inside the permanently shadow region and the counting rate outside the permanently shadow region. It was found that the correspondence shows that counting rate Newton flux inside the permanently shadow region is less than the outside Newton flux outside the permanently shadow region, approximately about the 2%, which is not so significant value as we may expect. So our conclusion here that we have found that some large permanently shadow regions have the enhancement of the hydrogen, and for example in the Shoemaker we may predict that 250 ppm of the water equivalent and more than 500 ppm water equivalent in the Cabeos, and we are thinking that Shoemaker and the Cabeos are the best candidates for the permanently shadow region with the water ice. For example, if we will use a more sophisticated model of the distribution of the water in the Cabeos, using the double-layered model with the poor hydrogen material on the top and the rich hydrogen material on the bottom, we may predict the weight percent of the water equivalent in the Cabeos, which is comparable with the direct estimation from the L cross. But also we may say that there is no statistically significant difference of the Newton suppression for most of the largest permanently shadow region in comparison with the local sunlit surrounding, but we may say that they tend to demonstrate some small less neutron emission than the surrounding areas, and this changes is as high as a 2% in the Newton flux. So continue this subject, we may postulate the task number 2, which is stated here by the red. The major goal of this task is just to search for the local Newton suppression region based not only known a priori information about the permanently scheduled region, but just to try to search the so-called Newton suppression region, which is based only the distribution of the Newton flux, which is observed by land. Schematically, it looks like the following. Then we try to find the local spot at the polar region on the moon, which shows all significant depressions in Newton flux in the comparison with the surrounding, or the excess of the Newton flux in the comparison with the surrounding areas. We have made this estimation, and this is the result of this analysis presented for the north and for the south. The blue areas correspond to the found Newton suppressed regions, which demonstrate the significantly less Newton flux inside this region in comparison with the outside vicinity of this region. It is interesting that several of them, like this one or this one, are located close to the known permanently scheduled region, like the Shoemaker, which is here, and the Cabeos, which is here. But these regions do not coincide exactly with the contours of the permanently scheduled regions. So this is the illustration of this fact for the Cabeos area. This is the Cabeos contour of the permanently scheduled region, and this is the red and blue contours derived from the land data for the Newton suppressed region around this area. The contours correspond to the different observational time. The blue one is based on the first half of the LRO mapping, and the red one corresponds to the full LRO mapping for the 2 years of the observations. This is the summary for the found at Newton suppressed region, and here we try to put in the one table not only the estimation of the suppression or the excess of the Newton flux in this region, but also try to compare it with the local parameter which may be derived from the other experiments like the Lola and the Diviner, and to compare it with the illumination, the temperature, and we try to compare the value of the temperature inside the Newton suppressed region and the temperature outside this Newton suppressed region in the latitude belt, which is include this suppressed region. And the same to do it not only for the temperature but also for the illumination. And results of such analysis presented on this slide. This is the chart. The x-axis correspond to the temperature, absolute difference in the temperature. The difference in the temperature inside of the found the Newton suppressed region or Newton excess region, and the temperature outside this region. So a negative temperature means that in given Newton in given region we found the less temperature than the outside this region, and the positive temperature means that this region is hotter than the outside territory. And the y-axis correspond to the suppression of the excess of the Newton flux inside the founded spot. The negative means that in the given spot we see the less Newton flux than the outside the spot, and the positive value means that in this area we see the larger Newton flux than the outside of this area. So looking at this chart, we may say that there are several regions which shows that negative neutron suppression inside the region may be combined with the observation that the temperature inside this region also is less than the temperature outside this region. And again, for the some spots, we see the excess of the neutron flux, which is followed by the excess of the temperature. So here we may postulate that for several founded neutron suppressed or neutron excess region, we may say that there is some kind of the low, that less local irradiation, the lower temperature correspond to the less local neutrons emitted inside this region. Okay, I'm actually done.
Okay.
So this is the conclusion to this part. The first one, that analysis of the land maps of the epithermal neutron emission at the lunar poles shows that there is effect of the significant variation of the neutron emission at the local spots, and we call the spots as the neutron suppression region. Then we see the suppression of the neutron flux in the neutron excess region. Then we see the excess of the neutron flux inside the spots. We also may say that some of these neutron suppressed regions are located in the vicinity of the permanently scheduled regions but do not coincide with them. And this is a statistically supported statement. Also, we can say that all selected spots have been studied using the independent data for the solar radiation from the LOLA data set and for the average surface temperature taken from the diviner data. And we found that some neutron suppressed regions have significantly different temperature and illumination if we compare it with the average estimation for the corresponding latitudes. We may combine this observation in the following statement, which means that this suppressed neutron region follow empirical law that less local irradiation, lower temperature may mean that fewer local neutrons emitted inside this region. And we assume that the hydrogen quantum is the driving factor for this law. Thank you.
Thanks very much, Max and Bill. We have time for maybe 2 questions. I believe that Hawaii is now back on. So any questions? Larry, if you could wait for the microphone.
I would expect that based upon diviners' temperatures and that maybe, I don't know, just intuitively, I would think that the lowest temperature you would find would have the highest amount of hydrogen signal. That doesn't seem to be the case, however.
I might say the following, that we definitely speak it to the mic. Yeah, thank you. I might just repeat the following, that we definitely found the spots on the poles which are not coincide with the permanently scheduled region with the lowest temperatures, but which may be close to them, which shows that we see the low neutron flux inside the spot, which correspond to the low temperature in this spot. It's not as low as predicted for the permanently scheduled region, but it is significantly low than the surrounding. For example, for some spots, we see the average temperature inside something like 60 or 70 kelvins, but the outside temperature is significantly larger, which is more than 100 kelvins. So and another issue that if it's not, it doesn't work for the old spots which we found, but for some of them we may look at the diviner map, which is not exactly the temperature map, but this is a prediction how ice may be located deep on the surface. And we see that it partially interlaps with the prediction of the diviner that in this particular places the water ice from the temperature condition may be located not on the top, but at some depth. So we may say that probably we see the traces in our neutron data, we see the traces of this water ice which located at some depth in this particular region.
I tell you what, why don't we thank our speakers.